Welcome to O2O, the out-of-the-office investigation into personal health, understanding, and actualization. I'm Mason.
And I'm Bobby. And today we are really stepping outside the office. Way outside. We're going to investigate the very nature of reality itself. We're talking about a journey from how our own brains quite literally build our world, all the way to the absolute craziest frontiers of physics, things like quantum mechanics, string theory, and yeah, even the multiverse.
You know, it really all kicks off with this quote. It's just incredible. It's this paradox that sits right at the very heart of what we're exploring today. The world is definitely real, but what we experience, well, that isn't the real world. It's more like a model, an interpretation, or maybe even a user interface.
Exactly. And Bobby, that distinction is absolutely everything. It's the difference between the map and the actual territory. Philosophers have been debating this for centuries, but now neuroscientists and physicists are handing us the tools to explore that gap in ways we just never could before.
So, here's our game plan for this investigation. We are going to start with the most personal piece of this whole puzzle, our own minds, and how our senses construct the world we live in every single day. Then, we're going to peel that layer back to look at the universe's, let's call it, operating system, and we're going to find a deep, deep conflict at the heart of modern physics. From there, we'll dive headfirst into the truly bizarre rules of the quantum world, and then we'll join the hunt for a theory of everything that could finally put it all together. And trust me, that hunt leads to some seriously wild ideas. We're talking hidden dimensions and other universes. But don't worry, we're going to bring it all back home and explore how these massive cosmic ideas can actually have an impact on our own well-being.
Okay, let's get right into this first part. Bobby, in that physics forums discussion we looked at, someone brought up a really simple but honestly profound example. A candy bar. When you see a candy bar, what are you actually experiencing? Is it the candy bar itself?
Not even close. What you're experiencing is your brain's interpretation of a bunch of signals. That's it. Light bounces off the candy bar, it flies into your eye, it becomes an electrical signal that your brain then processes into what you call an image.
The exact same thing goes for touch, taste, smell, sound. All of it is happening inside your head. And this right here is the core dilemma. We can't step outside of our own consciousness to check our work, can we? Our entire experience of an external world is built from purely internal signals. We put all this trust in our senses, but we know they can be fooled. So how do we know this isn't all just a really, really convincing dream?
Is a fundamental question for sure. We are literally locked inside our own perceptual theater, and we're just watching a play that our brain is directing, producing, and starring in. Every single color, every sound, every flavor is a creation of our own neural hardware and software.
This slide just illustrates that divide perfectly. On one side, you have objective reality, the universe as it actually is, completely independent of any mind looking at it. That's the realm of physics. But on the other side, you've got perceived reality, which neuroscientists have started calling our user interface.
Oh, I love that analogy. It's perfect. Think about it. The icons on your computer desktop aren't the actual files and folders buried in the code. They're just simple pictures that help you use a really complex system. Well, it's the same thing with our senses. The redness of an apple or the sweetness of that candy bar aren't actually properties of the objective world. Their icons are brain made up, designed by evolution to help us survive, to find ripe fruit, to stay away from poison. It's optimized for action, not for showing us the raw, unfiltered truth of reality.
And if you follow this idea to its logical and, pretty extreme conclusion, you land at solipsism. It is the ultimate skeptical position. What if my mind is the only thing that actually exists, and everything else, the world, other people, even you, Bobby, is just a projection inside of it?
Right. It's a fascinating thought experiment, mainly because you can't prove it's wrong. There's no way to falsify it. But while it's a fun philosophical rabbit hole to go down, it's not super useful for living your life or for doing science. To make any progress, science has to make a pragmatic assumption that there is an objective reality out there that we can investigate, even if we can only ever see it through our own weird filters.
Which brings us to the perfect transition. If our perception is the user interface, the icons and windows we click on, then what's the underlying code? What's the fundamental operating system that's running the objective world underneath it all?
And that question, Mason, takes us right out of the realm of neuroscience and philosophy and drops us smack in the middle of modern physics.
So to try and understand this operating system, physicists in the 20th century came up with two incredibly successful theories that are, unfortunately, fundamentally incompatible with each other. These are the twin pillars of modern physics.
And as you can see, they govern completely different domains. On one hand, you have Einstein's general relativity, our theory of the really, really big. It describes gravity as this smooth, continuous fabric of space-time. This is the world of planets, stars, and galaxies.
And on the other hand, you have quantum mechanics, our theory of the very, very small. It describes the world of atoms and particles as a bizarre, lumpy, and probabilistic place. It's a whole different ballgame. And this conflict it's stark. General relativity is smooth and predictable. Quantum mechanics is chaotic and uncertain.
You're listening to OOTO, with research by author Paul Bulow.
And the universe is one place. The rules can't just be different depending on whether you're looking at something big or something small. This whole clash becomes completely unavoidable when you try to describe things that are both incredibly massive and incredibly tiny, like the center of a black hole. When you try to use both sets of equations there, they just completely break down. They give you nonsense answers, like infinities. And this is the critical point. This incompatibility is like a giant flashing sign telling us that our understanding is missing a huge piece of the puzzle. Just like Arvin Ash puts it, we don't live in two realities. There has to be some deeper, more fundamental theory that both general relativity and quantum mechanics just emerge from.
And finding that unified theory, often called a theory of everything or quantum gravity, well, that's the single greatest challenge in fundamental physics today. And to even begin that search, we first have to really appreciate just how mind-bendingly strange the quantum side of reality truly is.
So, welcome to the quantum realm. If our perceived reality is the user interface, and general relativity describes the large-scale layout, then this is the machine code. And I've got to tell you, it is deeply weird. The logic of our everyday experience just goes right out the window here. It really is a completely different world. It's governed by principles that honestly sound like they were pulled straight from science fiction. But here's the kicker. They have been experimentally verified to incredible, unbelievable degrees of accuracy. So let's look at a few of these core ideas. First up, superposition. This basically says a particle, like an electron, doesn't actually have a definite location until you measure it. Instead, it exists in a kind of cloud of all possible locations at once. Then you've got the Heisenberg uncertainty principle. This is a fundamental limit on what we can even know. The more precisely you measure a particle's position, the less precisely you can know its momentum, and the other way around. And it's not because our instruments aren't good enough. It's a built-in feature of reality itself. And maybe the strangest of all is quantum entanglement, which Einstein famously called spooky action at a distance. You can link two particles so that they share a single quantum state, and then, no matter how far apart you pull them, across a room or across the entire galaxy, measuring a property of one particle instantly influences the corresponding property of the other. It's wild. When you take all of this together, you arrive at just a staggering conclusion. The solid, predictable cause and effect world that we all experience is, in a way, an illusion. Fundamentally, reality isn't some clockwork mechanism just ticking along a predetermined path. No, it's a game of chance.
That's exactly right.
The very bedrock of existence is this shimmering sea of probability and potential. An electron isn't at a specific point. There's just a probability of finding it there if you decide to look. And this probabilistic nature is what fundamentally clashes with the smooth, deterministic world of Einstein's general relativity. So how in the world do we bridge this massive gap? Well, the first and most successful attempt to describe the quantum world is a framework called quantum field theory, or QFT for short.
And this is a truly monumental achievement in human thought. QFT completely reimagines the universe. It's not about tiny particles zipping through empty space, but instead, it's a collection of invisible fields that permeate all of reality.
Okay, so in QFT, there's an electron field that's everywhere in space. What we think of as an electron particle is really just a localized vibration or an excitation in that field. And the same thing goes for every other fundamental particle. The absolute masterpiece of QFT is the standard model of particle physics, which successfully describes all the matter particles we know of and three of the four forces: electromagnetism and the strong and weak nuclear forces.
And the standard model is, you could argue, the most successful scientific theory in all of human history. I mean, its predictions have been confirmed by experiments to an absolutely astonishing degree of precision. But like we've said, it has this huge glaring hole in it. It's completely missing gravity.
And there's another really deep puzzle right at the heart of the standard model, and it's represented by this number, 19. These are what they call the free parameters. They are fundamental constants of nature, things like the mass of an electron or the strength of electricity, that the theory itself doesn't predict.
That's right. To make the equations work, physicists have to go out, measure these 19 numbers in experiments, and then literally plug them into the theory by hand. The theory gives us zero reason why they have the specific values they do. They just do. And this leads to this profound mystery called the fine-tuning question.
Yeah, it seems like these 19 constants are exquisitely, perfectly tuned for a universe like ours to even exist. If they were even a tiny bit different, the cosmos would be completely sterile. Why? QFT has no answer. You're listening to OTO, with research by author Paul Bullo. And this is where a radically new idea enters the picture: string theory. String theory starts with a fundamentally different assumption. It says if you could zoom in on any particle, way, way down, you wouldn't find a point. You'd find a tiny vibrating loop of energy, a string. And its biggest claim to fame is that one particular vibration of that string naturally corresponds to the graviton, the quantum particle of gravity. So gravity, the thing that's missing from QFT, just sort of pots out of the theory naturally. So the core idea of string theory is just beautiful in its simplicity. Think about a violin string. It can vibrate at different frequencies to produce different musical notes. Well, these fundamental strings vibrate in different patterns. One pattern of vibration looks to us like an electron, another pattern looks like a photon, another a quark, and another a graviton. All the particles and forces we see in nature are just different notes being played by these tiny little strings.
It's an incredibly elegant and ambitious vision for a unified theory, but to make the mathematics work, it comes with a spectacular, non-negotiable requirement, one that forces us to completely rethink the nature of space itself. String theory requires that the universe doesn't just have the 3 spatial dimensions we all know and love. It needs more, a lot more.
So where are they? Well, the classic way to visualize this is the garden hose analogy. If you're standing really far away, a garden hose just looks like a one-dimensional line. You can only move forward and backward along its length. But if you get right up close to it, you realize there's a second dimension, the little circle of the circumference that you can move around. String theory proposes that these extra spatial dimensions are just like that circumference. They are compactified, or curled up on themselves at a scale so unimaginably tiny that we can't possibly perceive them in our big macroscopic world.
Now, what's so fascinating is that the theory suggests that the precise shape of these tiny, curled-up dimensions determines, well, everything. Their geometry dictates how the strings are allowed to vibrate, which in turn sets the values of those 19 finely tuned constants we were talking about earlier.
But here's the catch. The theory doesn't predict just one shape. It allows for a staggering number of possibilities. The latest version suggests there could be as many as 10 to the 500th power different possible shapes for these dimensions, and each one would correspond to a different universe with completely different physical laws. This gives rise to the idea of the multiverse, not as science fiction, but as a direct consequence of the theory. We would just be living in the one universe whose specific geometry happens to allow for our kind of existence.
But Mason, I have to jump in with the skeptical note here. It's an unbelievably compelling idea, but we have to remember this is all deeply theoretical. String theory has yet to make a single testable prediction that has been confirmed in an experiment. The existence of extra dimensions or other universes is, for now, pure speculation.
That is a crucial point. And before we get completely lost in the multiverse, let's talk about another profound what-if scenario about the nature of our reality: the simulation hypothesis. This idea basically takes the concept of a constructed reality to its absolute ultimate conclusion. What if our entire universe is just a program running on some unbelievably advanced computer?
Exactly. The philosopher Nick Bostrom framed this perfectly with his famous trilemma. He argues that just based on probability, one of these 3 statements on the slide pretty much has to be true. First option: civilizations like ours always go extinct before they get powerful enough to run these hyper-realistic simulations of their ancestors. Second option: any civilization that does reach that point of technological maturity simply loses interest in doing it. Or the third option, and this is the real mind-bender: if you think the first 2 are unlikely, then we are almost certainly living in a simulation. The logic is just statistics. If it's possible to create many simulated realities, then over time, simulated worlds would vastly outnumber the one base reality. So any conscious being is just far, far more likely to be in one of the simulations. Okay, wow. We have journeyed from our own inner world to the outer cosmos, from string theory to simulated realities. As we always do on OTO, we need to bring this all back to our actual lives. So Bobby, the big question: how can grappling with these enormous abstract ideas possibly affect our day-to-day well-being?
I think it can have a truly profound impact. For example, when we really start to grasp that the solid world isn't so solid, that at its core, reality is this dance of potential and probability, it can fundamentally change our relationship with things we can't control. It offers a totally new lens through which to view stress and anxiety.
So what are the key elements here? What can we take away from these theories for our daily lives? Well, the first thing is about embracing uncertainty. Quantum mechanics tells us, flat out, that at the most fundamental level, the universe is not a predictable clockwork machine. It's uncertain. For anyone out there who struggles with anxiety or a need for control, truly internalizing that can be incredibly freeing. It's about learning to be comfortable with probability instead of demanding an impossible certainty from life. And I think the multiverse concept, as wild as it is, offers a powerful dose of perspective. When you really zoom out and consider that your reality might just be one of countless variations, it can help shrink personal problems down to a much more manageable size.
So, can awareness of these concepts improve our mental health, relationships, and physical performance? I absolutely believe so. And understanding these ideas aligns our bodies to understanding truth and perception, which helps us to live in a healthy environment for both mental and physical success. Think about entanglement, that spooky action at a distance. It points to a deep underlying interconnectedness in the universe. If we apply that principle to ourselves, it reinforces a holistic view of health. It encourages us to see our bodies not as isolated machines, but as complex systems deeply integrated with our environment. From the diet we choose to the air we breathe, it's all one interconnected system.
And that sense of alignment is just critical. When we see our daily choices, what we eat, how we think, how we act, not as trivial things, but as our way of interacting with this vast interconnected system, it gives them more weight. So an awareness that aligns healthy daily choices for diet, behaviors, and medical care is critical to our physical and mental health. It can even support recovery from conditions like hypertension.
That's a perfect way to put it. This gives us a framework for what we could call cosmic well-being. It's not just about managing symptoms, it's about aligning our lives with the way things truly are, right from the quantum level all the way up.
You're listening to OTO, with research by author Paul Bulow. Ultimately, this expanded view of the cosmos can be linked to an overall healthy outlook and a more peaceful life. When you see the world as a place of infinite potential and deep interconnectedness, it suggests our body's health is connected to our diet, actions, nutrition, sunlight, fresh air, our personal energy, and having a clear routine where our actions, words, and thoughts are all in alignment.
And that brings us to our final provocative thought. String theory suggests that the fundamental constants of our universe, the actual rules of the game, could have been different. So, if the very laws that shape our entire cosmos are just one set of possibilities among countless others, what does that say about the limits we place on ourselves? If the universe is built on pure potential, what does that say about our own potential to change, to adapt, and to create our own reality within the one we inhabit? That's something to ponder, long after this investigation is over.